Hello, welcome to the lecture series on control systems engineering. Now we'll continue our discussion on mathematical modeling of physical systems. In the previous session, our focus was more on mechanical system. In this session, we'll take electrical systems. So first in this session, I would like to define some of the electrical quantities such as charge, current, voltage, capacitance, resistance, inductance. Then we'll develop differential equations, mathematical models, and also find transfer function for simple electrical circuits when they are in series and parallel configuration. Then we'll draw analogous circuit, electrical circuits for given mechanical systems using force voltage and force current analogy. At the end, let us develop mathematical models for armature control DC motor and field control DC motor. Okay, field control DC motor. So first let us talk about simple LRC circuit. Let us find the transfer function of the electrical circuit so that I can define all the quantities also. This is a simple LRC circuit. Like this is the inductance, resistance, and capacitance. EI is the input voltage. E0 is the voltage, output voltage, and I am taking this output voltage across capacitor. And I is the current. Like in mechanical, we consider mass, right, stiffness, and damping, right? The same way in electrical system, the LRC circuits represent most of the electrical systems. So that you can represent the electrical dynamic systems using these components L, R, and C. So here we'll use Kirchhoff's voltage law. So you know that input voltage EI must be equal to sum of the voltage drop across inductance, capacitance, and resistance. So what is the voltage drop across an inductance? It is given by L di by dt. Similarly, voltage drop across a resistor is given by IR. And voltage drop across a capacitor is given by 1 by C integral IDT. So voltage drop across inductance plus voltage drop across resistor plus voltage drop across capacitor is equal to input voltage EI. Okay, this one EI is equal to this plus this plus this. And current I is defined as rate of change of charge dq by dt. So let's substitute here. So you'll get L d square q by dt square R dq by dt. dq by dt, if I substitute dt will cancel. Integral of dq will become q by c, and input voltage Vi. Now if I take Laplace for this, assuming all initial conditions to be 0, you get L s square q of s plus R s q of s plus 1 by c q of s, which I can take outside. Correct? That must be equal to EI of s. EI of s. So if I take LCM of these things, it should become L C s square plus RCS plus 1 is equal to 1 of Q of S by C, and that must be equal to EI of S. Okay, that's what exactly I have shown here. LCS square RCS plus 1 Q of S by C is equal to EIFS. Now E naught I am taking across C, 1 by C integral of IFS. This can also be done 1 by C integral dq by dt. You cancel this, it is q by C, correct? So this q by C I can replace by E naught of S. So q of S by C I can replace by E naught of S. Then this will become E naught of S. Then E naught of S by EIFS is equal to 1 by LCS square plus RCS plus 1. This is a second order electrical system. Okay, second order electrical system. That's how we can find the transfer function of LRC circuit. Okay, right. Let us talk about force voltage analogy. What is it? Already we have studied this, model this mechanical system. Its differential equation is m d square y by dt square f dy by dt ky is equal to f of t. This differential equation we have already derived in the previous session. Just now we did. Its equation is L d square q by dt square r dq by dt plus q by c is equal to E of t. Let us compare this equation with this equation. Both are second order differential equations. Okay, in this case the forcing function is force, mechanical system. Here the forcing function is voltage. So the force can be represented by an equivalent voltage. Correct. So these are all forces, these are all voltages. This is the inertia force, this is a voltage. This is damping force, this is a voltage. Okay. So every force can be represented by an equivalent voltage. That's why it's called force voltage analogy. That means a mechanical system can be represented by an equivalent electrical system. Okay. So only thing is here you have mass, analogous to mass is inductance. Here you have damping, analogous to damping is resistor. Your stiffness, analogous to stiffness is 1 by C, reciprocal of capacitance. And force, voltage and displacement is represented by charge. Okay, that's why it's called force voltage analogy. Here you can see that I have represented mechanical quantities, their notations, and then I have equivalent electrical quantities and their notations. Right? Mass or mass moment of inertia, in case of it is a rotational system, M or J. It is inductance in electrical. So next is damping coefficient, F, if it is rotational, Ft, electrical resistance, and R. Stiffness coefficient, K, Kt for rotational system, reciprocal of capacitance. Okay, 1 by C. So displacement is y or theta, equivalent is electrical charge. Force, here force or torque, equivalent is voltage. That's why it's called force voltage analogy. Now here they have given a mechanical system. You have to draw an equivalent electrical circuit for that. It's very easy to solve, write equations for electrical circuits. So modeling becomes easier. That's the reason we follow all these methods. So how do we draw? M1 is equivalent to inductance. So I'll draw an inductance here. M2 is another inductance. Mark here. Okay, I connected this. To this mass M1, the spring is in series. So capacitor in series. Capacitor in series. Next, this damper is in series. Here also the resistance is in series. Next, this damper is in series. So here also this damper is in series. Correct. Between these two systems lies another capacitor. So the displacement of this can be x1 minus x2 or x2 minus x1. Accordingly, current should be q1 minus q2, whatever it is. Sorry, I1 minus I2 or I2 minus I1. So that's why I've shown capacitor here. And so also the resistor. Correct? The force is on this side and I have shown the voltage source here. So this is the current I2. So the displacement of mass M2 is x2. Now K2, the displacement is x2 minus x1 or x1 minus x2. So accordingly the current, suppose if this is the current I2 and this current is I1 and this current should be I2 minus I1. I2 minus I1. Okay. So that way I have written down. So this represents this mechanical system. Thus, you can make use of this force voltage analogy concept and you can convert a complex mechanical network into an electrical network. Now in these examples, I have shown three rotational masses. Correct. So J1, there should be an inductance. J2, there is another inductance. J3, another inductance. This resistor is in series, so show the resistor in series because the same current will flow here. Resistor in series. Resistor in series. Okay. Now in between you have this one. So in between C1. In between you have C2. This is in series. So R. So there is torque here. So here voltage. So again I have converted this mechanical circuit into an equivalent electrical circuit. If you are not understood, please see that force is applied here. J1. Okay. What is its displacement? Theta 1. So what should be the current flowing through that? I1. Now what is the velocity of this? Yeah, theta 1 dot. So current should be I1. So accordingly current is I1 here. Here what is this? This side is theta 1, this side is theta 2 is the displacement. So difference in current should flow. So this is I1 and current that is flowing in this circuit is I2. The current that is flowing here is I1 minus I2. So that way you get the difference. That's how we can write the circuit. We can draw the circuit. Now let us put LRC circuit. Let us consider in a parallel arrangement. Let us say I have a current source. I have inductance, resistance, and capacitance. E is the voltage. So, what is the current flowing through this inductance? IL is 1 by L integral of E dt. Already I told you U is nothing but L di by dt, correct? So IL is E dt 1 by L E dt, then you can integrate it. You'll get this from this equation. The resistor is E is equal to I by R, so IR should be E by R. Similarly, E is 1 by C integral IC dt. If I dE by dt, if I make it differentiate, then IC by C get cross multiply, you'll get this. So since I know the voltage values, I can easily find out what are the current values. So according to this, the total current must be equal to current through this plus current through this plus current through this. So the whole equation is IL plus IR plus IC must be equal to I total. Correct? Voltage is same. So now I substitute for IL, then I'll substitute for IR, then I'll substitute for IC. Correct? IC. But what is E? E is nothing but rate of change of magnetic flux. So d phi by dt. You can say d psi by dt. Psi is magnetic flux. So substitute here d psi by dt. You will get an equation like this. Correct? This is also a second order differential equation. You can compare this equation with m d square y by dt square plus c dy by dt plus ky is equal to f of t. Now the force is represented by its current. So that's why it's called force current analogy. These are current values, these are force values. Okay, so now analogous quantities are m is represented by c, damping coefficient is represented by 1 by r, and stiffness is represented by 1 by L. These are the analogous quantities. Right? Now, that's what I have done. I have written down the differential equation for electrical circuit, written down for the mechanical circuit, compared this, and I have listed out the analogous quantities. You can see for mechanical, electrical. This is what I mentioned. Correct now? Right. So now, once a mechanical circuit is given, you have to convert that into an electrical circuit using force current analogy. Correct? So let us look at this one. What you can do is mass is equivalent to capacitance. So I have drawn this. So these are in series, means here they should be in parallel. You can observe with that circuit also. Correct? You see here, sorry. Here the mechanical components are in series, but the electrical components are in parallel. So same way, here these mechanical components are in series. So this should become C1, K1 should become 1 by what? L1, K is 1 by L, correct? So, right, K is represented by L, damping is represented by F1 is by R1, and this damping is represented by this R. These are all in parallel. Okay, now let us consider this part M2. That's what I have shown here, C2. And this resistance is in series with this. This resistance I have shown, series. Now, between these two, we have spring. So there should be spring is equivalent to inductance, isn't it? So spring is equivalent to inductance here. So that's why it's shown inductance there, and damper is represented by resistance. These two are common to both the circuits. So now this mechanical circuit is represented by this electrical circuit, and this is each force is represented by an equivalent current. That's why it's called force current analogy. Okay, now let us try transfer function of an armature controlled DC motor. These armature DC motors, servo motors are very much useful in control applications. That's why it is better to learn how to model them. Okay. Here, as for the motor, you will have an armature and you will have a field. Here I am keeping the field current constant. Field current constant. Okay. So only armature current is varying. You can see this. This is the motor. This is the armature inductance, armature resistance, the input voltage, this armature current. This motor is driving a mechanical system. This motor will develop a torque T, and this is the rotating mass, and there are bearings and the damping over here. Okay, this motor is driving a mechanical mass. Okay, now to write the differential equation or mathematical model, let us consider this part of the circuit, the electrical part of the circuit. What is the electrical part of the circuit? The input voltage EA must be equal to voltage drop across inductance plus voltage drop. This is what you call it as, here we have a back EMF and then voltage drop across resistor. So what is this back EMF? When the current passes through the motor I, a magnetic field will be produced around this coil. Suppose this coil is rotating, it will start cutting its own magnetic field that will induce an EMF which opposes the incoming EMF. This we call it as back EMF. That is what it is. So input voltage EA must be equal to voltage drop across inductance plus back EMF plus voltage drop across resistor. So EA must be equal to LA DIA by dt plus IA RA plus EB. Correct? So input voltage EA must be equal to LA DIA by dt plus EB plus IA RA. But this back EMF depends on the rate of cutting. So EA must be directly proportional to d theta by dt, rate at which it cuts. Sorry, not EA, EB, back EMF, sorry. So EB is equal to, I will say, KB d theta by dt. Correct? Okay, rate of cutting. Here again I made a mistake here. It is EB. EB. Okay, please correct. And there is, when I develop a relationship between EB and d theta by dt, I will get a curve. From that I can get this slope, and that is what you call it as back EMF constant. Okay, fine. These are the two equations. Now let us consider the mechanical part of it. If you see the mechanical part of it, which I have already explained, T is the torque which is acting in the clockwise direction. So let me write here, T is equal to, for that there is an inertia force in this direction. So that must be J d square theta by dt square plus, there is damping, so F d theta by dt. This is another equation. Now torque depends on armature current. So I can say torque is directly proportional to IA, or torque is equal to KIA. Okay, this is another constant which relates torque and armature current. So thus I have got the four equations, right? Tj d square theta by dt square ft and T is equal to Kia. So let me list out all the four equations, right? Done. Now we'll take Laplace for each one of these equations. When I take Laplace for this, E of s is equal to LAS IA of s plus RA IA of s, and the TB I have replaced by KB d theta by dt. So it becomes KBS theta of s. Now T I have replaced by KIA, correct? Then this becomes KIA J d square theta by dt square plus FT theta by dt, and again I'll take Laplace. This will become K IA of s J s square plus Fs theta of s. From this equation, I can find IA of s, which is nothing but this one. So I will substitute this one for IA of s into this. Okay. So then you will get this LAS RA J square plus Fs theta of s plus K KBS theta of s. Take LCM now. You will get this. Output is theta of s, input is IA of s. You will get the transfer function of an armature controlled DC motor. Very, very useful relationship. Please keep it in mind. We'll use it in subsequent chapters. Okay. So if you are not understood, I'll just summarize. Write equation number 1 considering this. Establish the relationship between T and EB, the second equation. Write the mechanical equation and establish the relationship between T and IA. I think I messed it up. So write equation 1 involving L, EB and RA. Okay, you'll get one equation. EB depends upon the rate of cutting. So EB and theta related, second equation you write. Third equation you write the mechanical equation. Fourth equation, torque and current are related, write this equation. Then take Laplace, make the substitution and finally get the theta of s to E of s. Overall output of the system is theta, overall input is EA, get the relationship between theta of s to E of s. So you will get this equation. Similarly, we'll find transfer function for armature control, a field control DC motor. In this case, armature current is constant. See here, I am keeping the armature current constant. So since it is current constant, I do not have to write the equations for this. This is not varying at all. It's not in dynamic condition. Right. This is a field circuit. So you write one equation for the field circuit for exciting this. Okay. Field. Then this is the mechanical circuit. You write this. Of course, and the third equation is torque and this current should be related. Okay. Now, considering the field circuit, you will get EF is equal to LF DIF by dt plus IF RF. Please know the fundamental first problem. Like then it becomes very easy to understand this. Then take Laplace, you will get this. Next. From the mechanical system, J d square theta by dt square plus ft theta by dt. T and these are related, write this. Again, this T you replace by KIF, you get this equation and take Laplace, get IFS. This IFS value, you substitute in this equation. See here, in this equation. So when you substitute that, you will get E of s is equal to this equation after substituting. Then the output is theta, input is E of s, and you will get this relationship. That becomes the transfer function of field control DC motor. Now is an exercise, a simple exercise. Find transfer function for the system shown. What I have done is I have given two LRC circuits. Right, this one, this one. And I have given Vi as the input, V0 as the output. If you consider this part of the circuit, Vi is equal to I1 R1 and 1 by C1 integral of I1 dt. No, here the current passing is I1 minus I2, correct? Here the current will be I1 and this current is I2 and the current is I1 minus I2. So 1 by C1 integral of I1 of t minus I2 of t. Okay, that is one thing. Second, let me assume this voltage as V of t. This voltage V of t must be equal to 1 by C1, nothing but this. Okay. V of t is also equal to I2 R2 and this voltage, nothing but V0. Nothing but V0. V0 is nothing but the voltage drop across C2. So that is 1 by C2 I2 dt. You have to get now V0 of S by Vi of S. Take Laplace of each equation, make appropriate substitution and finally get the equation. This will be a first order equation, this will be a first order equation, totally it should become a second order equation. Second order system. Okay, I think now any number of branches if I introduce, you can go on, writing the equation and you can find the transfer function. Good. That's how we can find the transfer function of simple electrical systems. Now, thank you. We'll meet again.